Hello and welcome. Today we're going to be talking about object motion with gravity and air resistance. So to start, we want to go into the equation for motion. And it's always going to be F equals ma, as we've all know and love. And a of t, then, we can write down is, in this case, we're going to say that that's equal to the velocity of t prime. Okay. Likewise, we'll say that that y of t is the position, and y prime of t, of course, is v of t. Okay. And of course, and I hadn't written this down, but that is velocity. And of course, y of t in this case we're going to call vertical, a vertical position. And likewise, in this case, because we're talking about a gravity and the idea of falling objects, velocity will be a vertical velocity. Vertical velocity. All right, and we're going to have the convention that when v is negative, that means falling or downward motion. Okay, so with those conventions put into place, let's talk about the case where there is no air resistance. So case 1 is the standard case we're very familiar with, and that is where there's no air resistance. And no air resistance, then your F equals ma equation. F in this case will just be gravity, mg, and we're going to put a negative sign, which means downward motion, and that is so that's gravity. In this case, we'll say that g is equal to 9.8 meters per second squared. Okay. So that's true, and then what we have then is our dE then that results is going to be m v prime is equal to negative mg, and we can reorient this or sort of redefine, and then just put it in terms of the equation of acceleration only as v prime equals negative g. And what's important here is you see that without air resistance, there's no dependence on mass. Okay, so no dependence on mass, and that and that is a special feature of when we have no air resistance. All right, so this is a fairly simple equation to solve. We have to have some initial condition, which we'll just say is v of t equals 0 is equal to v naught, in which case then we can integrate this. So this is a directly integrable function, or a differential equation. So v prime dt is equal to negative g t plus c, in which case that becomes v of t is equal to negative gt plus v naught. Okay, so there's our solution, and we see that this is just downward motion, but we see that it's increasing. Because g is a positive number, we see basically we get this speed up. The speed up to infinity, or I should say negative infinity, as t goes to infinity. We can also analyze this equation and look at this equation a little bit more. We can look at it in terms of a phase diagram. And the phase diagram is pretty straightforward. I'm going to make my phase diagram, and again, the idea here is we want to look for points where v prime is equal to 0, and we clearly see there is no such points. In which case, what we have here then is we see that the velocity is the derivative of velocity is always a negative number. there are no equilibrium points, and so it just goes down like that forever. Okay, so that's a a really simple phase diagram right here. All right, so now let's talk about a different case, one with air resistance. So now we're going to talk about case 2 with air resistance. Okay, so what we need to do now is, what this amounts to is basically having, now we have two forces acting on the mass. So one way you can think of this now is, so we write down again F equals ma, but now F is going to be, again, two forces. One is going to be, again, just like before, gravity, negative mg. Right? But now we're going to have a plus Fr, this air resistance. So Fr is this air resistant force. Now it should go in the opposite direction of gravity, or it would go in the opposite direction of velocity, I should say. So the picture we have in our head now is we can think of some sort of parachute, and then there's a mass, and it should also, in some sense, the mass should depend on how this air resistance force works. Because if I have a little mass with a parachute, it should go slow. Whereas if I have the same parachute now, but then I have a big mass, it should go faster. And that's just, I haven't actually done any mathematical analysis of that. It's just something we know from our basic understanding of the world, that that it should be that our, so we saw in the previous case that the motion did not depend on the actual mass of the object that was falling, because there's no air resistance. But we know in our real world, our common understanding of how the world works, that it should be that a bigger mass should fall faster given the same air resistance and gravitational pull. So what we can do now is write down an equation that, so the force of air resistance in this case 2, we're going to say is going to be called a linear force, and Fr is equal to negative kV, where k then is this positive constant that is a drag coefficient. And now it turns out, and we call this a linear force here, and it's linear because, of course, it's a first power of v, and it turns out in practice, linear forces, linear drag, if you will, linear drag works for low velocity. So when velocity gets extremely high, it turns out that this model breaks down. It doesn't quite account for behavior as well. But as provided our parachute's big and we're not going too fast, this linear force of air resistance works pretty well. So now let's write down our differential equation. Of course, it's going to be mv prime is equal to negative mg. So this is the dE here. mg, that's our gravitational pull, and then in addition to that, now we have a negative kV. All right. So one thing I want to, so this is an equation of forces. So this is a force balance equation. But I can rewrite this now as an acceleration equation. And I can do so by essentially just dividing by m. So now we have v prime, which is acceleration, is equal to negative g minus k over mv. So here's the thing here. We see that the coefficient now on the linear term involving v depends on both this drag coefficient, which is related essentially to the size of the object and how resistive it is to air. So in this case, like how big your parachute is, essentially. And it's divided by the mass. So we see now that in this equation, this depends on the mass, just as our intuition would have suggested that both the size of the parachute relative to the mass of the object determines the speed, it's fast or slow. And we see that in there with the ratio of k over m. So this is our acceleration equation. So now let's go through it again. We have, just as before, v at time 0 is equal to our initial velocity. So let's now solve this equation. Of course, this is a first order linear equation. So we have v prime is equal to negative g minus k over m v. In the textbook, they give this coefficient, we call it rho. And that's in the textbook. And that's just the ratio of that drag coefficient over mass, just so you get that notation down. But I'm just going to leave it as k over m. It's a bit more illustrative. Okay, so here's our differential equation. We can move that part over so we have v all on one side of the equation. And we can clearly see that that is our p of t, and this is our q of t in terms of in the vernacular of the first order differential equation. So our rho of t, our integrating factor, is simply going to be e to the integral of p of t, which will just be e to the k over m t. We then can wrap this up, and we've done this many times now, so we're pretty good about it. Oops, I forgot one part there. That shouldn't be prime there, right? Prime should be on the outside, and that will be negative g e to the k over m t. All right, and now the next thing we need to do is integrate both sides with respect to t. And then add a plus c there, and we get v of t e to the k over m t is equal to, and then we have to take the antiderivative there, and that leads to a gm over k. And that's a curious constant because it looks like there that is that gravitational force divided by the drag coefficient. So that's an interesting piece there. And then we just solve for v of t, and we get negative g m over k plus c e to the negative k over m t. All right, so when we incorporate the initial condition, it turns out we can rewrite this as negative g over m divided by k plus, and what will we have to put there and where that c is to make this work out? Well, we see we have this constant term here, so we actually need to, and it's subtracted, so we need to add that back. And then we need to go plus v naught. Okay, so see if that works. If I put a t equals 0 in there, this becomes 1, plus and minus that, and we're left with only v naught. Now, of course, as t goes to infinity, we see that v of t is heading towards negative g over m k. All right, so this is what we call the terminal velocity. And it depends on both m, the drag coefficient, and the gravitational constant all put together. And the negative sign is just a convention that we are going downward. All right, one thing we can do is also look at this as a phase diagram. And we can see pretty clearly that I want to know where that thing is equal to 0. And of course, we can find that the critical point is, of course, exactly the equilibrium solution here, the solution that we're tending towards. It's negative g times m all over k. And that is the equilibrium. And so what we have here for a phase diagram is negative g times m over k. That's our v star. And if we start at a smaller velocity, maybe v equals 0, we can go down. We're going towards it. Likewise, if I start at a faster velocity, the drag force will eventually slow us down until we get back to that terminal velocity, right? And so we can say that that is stable. And that's what we already got with over here. We see that as time went forward, we were heading towards this terminal velocity, which is, it just squares with our notion of the phase diagram. Okay, so that's pretty good. And again, I think the important thing here is to say that FR, again, we're going to emphasize, equals negative k over v. And this is good for low velocities. Now, that's a relative term. What do I mean by low velocities? And we're talking about big parachutes. If I were to drop, and so that, but it turns out though, as if we didn't have a parachute and we're falling very quickly from the sky, that this model doesn't work very good. It doesn't provide, it doesn't accurately represent the forces as velocity gets higher. All right, so now let's go to case 3. And that's the case of where we have a nonlinear drag force. So in this case, FR is going to be equal to, and we're going to say that this is going to be a quadratic, or a quadratic drag force. So in this case, we're going to have negative k. Again, we have some drag coefficient times v times the absolute value of v. So obviously, what this represents then is, I can write this in a different form, and that is that if v is positive, right, that means that it implies then that FR is going to be equal to negative k v squared. Okay, and that means this is negative, right? We want this drag force to always go in the opposite direction of which we're traveling. Likewise, if v is less than 0, FR is equal to positive k v squared. Okay, and that means this is greater than 0. All right, again, the idea is that if we're falling, the force should be going up. All right, so so this looks pretty good. So now let's talk about. So we see that there's this piecewise definition here. So when we put down this equation, v prime is equal to negative g again. Now we're going to have a minus k v absolute value of v. If this is our divided by m, sorry. If this is our differential equation, we see that it certainly is nonlinear. And I'm going to put exclamation points. We have to, we have to be mindful of v changing signs. Okay, so what we're going to do now is consider the case of an object that's just falling downwards. So we're going to call it case 3, subcase A, which is v is less than or equal to 0. And this is the case where we have maybe v naught is equal to 0. We're dropping something off a building, say. We're taking this mass, Oh, excuse me. And we're just dropping it, and it's going downward. And so in this case, then, FR, we can take the case of, we have to take this latter case here. So FR becomes an upward only force, negative case. So it's a positive force in this particular case. All right, so let's write down that differential equation. It's going to be V prime is equal to negative G plus KV squared. All right, I'm going to do a little trickery here. I think it's good to set this thing up in a little bit cleaner way. I'm going to factor out a negative G. And then what I'm going to get is a 1 minus K over G V squared. All right, that looks pretty good. So now this equation, of course, is nonlinear, but we can use separation of variables. I think it's probably best to go to another page here. So let's try that. Let's go. Now we're going to write this down again. V prime is equal to negative G, all multiplied by V times negative K over G V squared. Right, and this is again the case where V is always it's non-positive. Okay, and this is our differential equation. We're going to use separation of variables. So what we have here is dV divided by 1 minus K over G V squared is equal to negative G dt. All right, and so we're going to integrate this. But the question is how to integrate that. That looks it looks a little awkward. So what we're going to actually do is do a little manipulation here. I'm going to go comma, and note that if I go, oh, you know what? I forgot something. There should have been an mg there, right? There need to be an m there. So I'm going to I forgot my my m. There we go. Sorry about that, guys. Yep, there was my m right there, and I forgot it. Okay, that looks better. So we need to put an m right there. Okay, that looks better. All right, so now our k over gm, and of course that right there was that this coefficient right there. It was the terminal velocity. So it's actually the inverse terminal velocity for the linear case. So that's something we log away in our minds. Anyway, what we have here is this k over g over m v squared. And we can rewrite this now as actually root k over gm times v quantity squared. All right, in which case then we can actually define the u substitution of u is equal to root k over gm times v, in which case du is equal to root gm over k. So that's du is equal to dv. All right. So now I can do this u substitution. We get to this point here of now root gm over k, which is that square root of the terminal velocity of the linear case, 1 over 1 minus u squared, and then we have our du. All right, so that's what we get for our integral. And you may or may not remember this, but this is one of those antiderivatives that's maybe buried somewhere in your mind. This is actually inverse hyperbolic tangent. And we're going to resubstitute back in u. We're going to get velocity over the square root of terminal velocity. So that's going to be, again, root gm over k. Okay. And that's equal to negative gt plus c. Okay, and that's from doing this integral here. All right, so the next thing we need to do is then solve this for v, and that's pretty straightforward to do. V of t is going to be equal to, and we have to go, now it's going to be, we have a gm over k, tangent hyperbolic tangent, c minus g of t. That was a little big there, sorry about that. And then we have, again, divided by root gm divided by k. Okay, so that's our v of t. And so the idea is, I mean, what does this look like? How does this differ from the linear case? And the nonlinear drag force applies higher forces, or higher drag, I should say, when velocity gets bigger. All other things being equal. And so this solution will reflect that aspect. One thing we should do is maybe look at a phase diagram of this. So let's do that. So again, let's go to v of t. V prime of t is equal to negative g plus k over m v and v squared, sorry. And we'll look at, again, at the phase diagram. So we have to find v values that solve this equation. And now what we see is so v. So this v value, then we have a square there. That's going to be equal to, again, mg over k square rooted, and then we have a plus or minus. Clearly now we can rule out. So the thing here is we need to rule out the positive value because we assumed v was less or equal than 0. So what we really want to just write down is that negative mg over k. So we should also then revisit this thing about mg over k. I said that this looks like the terminal velocity of the linear case. But it's not. It's different. And it's because k has different units, than in the linear case. Now that has to be true because this is velocity squared, so this k then has to be divided by a velocity in order to have the same units. So this is a per velocity drag coefficient in this nonlinear case. So we can't. There's no direct correspondence between the two, although the equations look, or sort of the final expressions look similar. At any rate, then what we have in this case is we have this this critical point, root mg over k negative, And again, we have the same issue where the same point where it'll eventually get stable at that point. Okay, and again, and this is all for v less than 0. Now, of course, in the other case where you have velocities going in the positive direction, there'll be some other equilibrium that's corresponding to the case where we have a positive velocity. But it turns out that in that case we have some instability. But we'll leave that for another time. Thank you very much.